Hi. You thought I wasn't here, but I am here. Or am I? You don't know. Hi. Today our topic of discussion is osmosis and diffusion. Those two terms we can group into a column that we call passive transport. It is important to understand that cells have to be able to move stuff. Okay? That's important. We can't survive unless our cells can move stuff. But there's more than one way to move stuff, which is why we are going to talk about both passive and active transport. And to do that, we need to establish our objectives. So let's take a look at what we are going to learn today. Now, if I'm going too fast, simply press the pause button and everything will stop. You can copy stuff down into your notes or whatever you need to do. All right? So let's take a look at our objectives for today. Our objectives for today are going to be to establish why diffusion is biologically important, define what osmosis is and why that is biologically important. We're going to explain the difference between the terms isotonic, hypotonic, and hypertonic. We're going to predict what would happen to a cell if it was placed in any one of those solutions. And finally, we're going to talk a little bit about active transport and a topic called facilitated diffusion. All right? So these are some topics that we will discuss. Now would be a good time to press pause and get these into your notes. All right, so let's go ahead and get started with a quick overview. As I've already said, materials need to be able to move into and out of and around inside a cell in order for things to function properly. All right, so materials have to be able to move not only into a cell in terms of maybe we need to get energy or maybe we need water, but cells also have to be able to get rid of stuff like waste. And also there are times where we make things in our cell that need to be in another part of a cell. And so all of that requires transport. There are several different mechanisms to transport things throughout a cell, but there are two major categories. The first category is that of passive transport, which is what we're going to talk about today. Later on, we're going to talk about active transport. Now, passive means pretty much what you think it means. If somebody's passive, it means that they don't really waste a lot of their own energy. Active, however, means that you are going to be wasting quite a bit of your own energy in order to get the job done. So passive basically happens by itself. It doesn't need any extra energy, whereas active means that you do have to use a little bit of energy. I'm going to go back, let you finish writing that down. I'll try to slow down so that you guys can get it all written down. If at any time you need to press pause, just press pause. Let's take a look at what diffusion is. Diffusion is a form of passive transport in which molecules move from an area of higher concentration to an area of lower concentration. What does that mean? Well, to put it in simple terms, diffusion is the movement of a substance where there's a lot of it to where there's a little of it. Yeah, I mean, it's the same thing. Just fancier words. You know, science people. All right. The difference in concentrations across the distance is called a concentration gradient. And I like to think of this as a slide, and I'll give you an example in a minute. But diffusion continues until equilibrium is reached. And equilibrium means that the concentration is the same throughout whatever we're dealing with. Okay? So that means that diffusion is going to happen when we have molecules that have a high concentration, I mean there's a lot of it, and there's an area where there's very little. They're going to move from where there's a concentration of a lot to a concentration of a little across a gradient. The bigger the difference, the bigger the gradient. And this process is going to continue until it's evenly distributed around the space. All right? So what do we really mean here? Well, let's give an example. We have here a molecule, okay? And here is our area. Here's where it's going to move, right? Well, if we put this here and we make only a little difference, just a little, you'll notice that the car moves pretty slowly, okay? It doesn't move a whole lot because there's not a lot of difference between this area over here and this area over here. Can you tell it's during school when I'm recording this? All right, so it doesn't move very fast, okay? There's just a very little difference. And of course, if I keep it flat, it doesn't move at all. That would be equilibrium. Now watch what happens if I do the same thing, but I make a really big difference. Really high concentration, really low concentration. I think I broke something. All right, you noticed how fast that went. Well, that's kind of how diffusion works. The bigger the difference, meaning this is high concentration and this is low concentration, the faster the particles will move. The less difference, the slower it'll move. So that's the concentration gradient concept. The bigger the difference, the faster the movement. Ah! All right. Now, concentration gradient, diffusion. Let's take a look at this in a molecular example, okay, now that I'm done playing with my toys. All right. Here's a look at what happens in diffusion. We have a high concentration here, and the particles eventually spread out and spread out and spread out until they completely fill the space. This is equilibrium. Diffusion can occur across a membrane, which means that molecules, if they can fit through, can move into and out of a cell. Because plasma membranes are semi-permeable, that means they can let some materials in and others not, it means that diffusion can occur across a membrane. Now, I am going to give you a couple more examples of diffusion. If someone in the back corner of the room there were to spray themselves with a wonderful smelling perfume, the person sitting next to them would smell it almost immediately. But the person sitting down here up front probably isn't going to smell it. But after a while, the concentration of perfume in the back corner will diffuse throughout the room until everybody gets a nice little hint of it. The same is true about fragrant candles, okay? And of course, less fragrant things. For example, if someone happens to have had beans last night, the same would be true, okay? If they accidentally had a moment, then everybody would go, But the person sitting next to them would smell it first, and then it kind of spreads. That's diffusion. It's science. It's not very pretty science, but it's science nonetheless. All right, so let's go back to our topic of diffusion. Now that we know what diffusion is, and by the way, I'm going to go back and let you see that animation one more time. Oh, it's not letting me do it. Never mind. Let's talk about osmosis. Osmosis is a specific type of diffusion, but it deals specifically with water. Osmosis is how water diffuses across a membrane, once again, from an area of high concentration to an area of low concentration. This is particularly important because water, as we have already learned in our biochemistry unit, is the most important and most common solvent in all living organisms, which means that water has to be able to move because it's the thing that we're all dissolved in. We are over 75% water, folks. Water's pretty dang important. That means it's got to be able to get around. The external environment at this point becomes very important because, as we've learned, water can move through a membrane. So if there isn't very much water around us, or if we're in an environment that would rob water from our cells, then it's possible that we will continue osmosis until equilibrium, which means our cells could dehydrate. That is an important topic. So let's take a look at osmosis here. In osmosis, we have the water particles moving through the cell. Obviously, the blue particles, by the way, being water, are a higher concentration over here than they are over here. Okay, that is, they are higher concentration in the yellow part than they are in the pink part. So the water molecules are flying across the membrane here in order to reach equilibrium. This process will continue until the concentration on the yellow side is the same as the concentration on the pink side. All right? Now, let's talk about some issues here. Let's say that my cells have a certain concentration of water, which on average they do. But let's say that I expose myself to somewhere where there is more pure water outside of my body than inside of my body. Well, the rules say that water will move from an area of high concentration to low concentration. Well, if my body has a lower concentration of water, then the water will flow into my body's cells. The opposite is also true. If I'm in an environment where my body has a higher concentration of water than the environment, the rules of osmosis say from an area of high concentration to an area of low concentration, which means the water is going to move out of my body at that point. So what we need to understand is that the external environment of a cell really does make a difference because it can determine whether we gain water, lose water, or if we are at equilibrium. All right, so let's talk about a couple more things specifically. To understand this next part, there are a couple of terms we need to review. First of all, the term solvent refers to a substance that dissolves in another. So if we're talking about salt water, the solvent, excuse me, I think I even misspoke there. Solvent is a substance that dissolves something else. So if we're talking about salt water, water is the solvent. That makes salt the solute. The solute is the thing that gets dissolved. I think I might have confused some folks, so let me restate that. The solvent is the thing that dissolves something else. The solute is the thing that gets dissolved, okay? When we talk about concentration, concentration is the amount of solute compared to the amount of solvent. So if we say a 10% salt solution, it means that we have 10% salt and 90% water. So in this case, a 5% saltwater solution is a solute in which the water is the solvent, salt is the solute, and that means if we took 5 grams of salt and 95 grams of water, we would end up with a 5% salt solution. All right, so why is this important? Well, let's take a look. A hypotonic solution is a solution in which the concentration of the solute is lower than the cytosol in the cell to which it's being compared. Okay? That basically means that this substance is closer to pure water than our own cells. Okay? So that means that there's less stuff in a hypotonic solution than there is in our cells. The opposite term is hypertonic. If a solution is hypertonic, it means it has more stuff dissolved in it compared to the cells. Okay? And finally, an isotonic solution is one in which the concentration of solute is the same as compared to the cells. So hypotonic is closer to a pure substance, okay? The purest hypotonic solution that I can think of compared to our cells is distilled water, okay? Hypertonic is complete opposite. It's got a lot more stuff dissolved in it than our cells do. Isotonic would be an example of, say, saline solution that you use for contacts. It is designed to have the same amount of concentration of salt in it as our cells do, okay? And that becomes important when we talk about movement, because if you have a hypotonic solution, that means you have a difference in concentration, which means you create a concentration gradient, which means osmosis or diffusion is going to happen. If you have a hypertonic solution, that means there's a difference in concentration, which means you have a concentration gradient, which means diffusion is going to happen. If you have an isotonic solution, it means there is not a difference in concentration. That doesn't mean that diffusion is not going to happen. It just means that we're going to be at equilibrium, which means as stuff moves one direction, stuff's going to move the other direction at the same amount. All right? So let's understand this clearly. All right? Hypertonic solutions have a lot of stuff in them compared to our cells. That means that our cells, comparatively, are purer than a hypertonic solution. Now, it's important to note the term hypotonic, hypertonic, and isotonic are comparative. We can't say, oh, look at this substance. This is a hypertonic, blah, 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 blah. It has to be hypertonic compared to something else, okay? So when we use hypotonic, hypertonic, and isotonic, traditionally we're talking about cells. That makes sense. So if I say I'm dealing with an isotonic saline solution, what I really mean is I have a saline solution that is the same concentration of salt water as is in our cells. Okay? If I say I have a hypertonic salt solution, that means it has more salt and therefore less water than our cells. If I say I have a hypotonic salt solution, it means it has less salt than our cells and therefore it has more water. Because you see, there is an inverse relationship, an upside down relationship between solvent and solute. If something has more solvent, it has less solute. If it has more solute, it has less solvent. That's called an inverse relationship. They are opposites. Okay, so that's what we're dealing with. Thank you, Mr. Doc, for that wonderful Mr. Wizard moment. The question is, why do we care? Why do we care that there are differences in concentrations? Because we understand that osmosis happens on its own. We can't stop it from happening. It's going to happen. So if we expose cells to concentrations of solutions that are different than the concentration inside the cell, water's going to move. And we need to be able to predict that. So let's take a look at what would happen in a cell if we exposed it to different solutions. In this first box, we've exposed this red blood cell to a hypotonic solution. In this case, pure distilled water. Water then is purer on the outside than it is on the inside, which means that water is going to go from an area of high concentration, which is outside the cell, to an area of low concentration, which is inside the cell. That means that water is going to continue to go into the cell, into the cell, into the cell, and ultimately the cell will lyse. The word lyse, by the way, if you recall from the study of organelles, we said lysosome means to destroy. Literally means that the cell blows up, okay? So what happens in a hypotonic solution is cells have the potential to increase in volume and ultimately their cell membrane gives way and they pop. That's what happens if you submerge a cell in a solution that is too pure. If you put a red blood cell in an isotonic solution, like saline for example, the amount of water going in and the amount of water coming out are equal, thus equilibrium. Now, there is an important note here. When we talk about isotonic solutions, it does not mean that water isn't moving at all. Oh no, as a matter of fact, water is moving, but it's moving in and out at the same rate, which means for every molecule of water that comes in, one will go out. That's why we reach equilibrium. Finally, if we put a solution in something like hypertonic solution, let's say we put it in a 20% salt solution, well, that means that there is more water inside the cell in terms of concentration than there is out. That means there's a higher concentration of water in the cell than there is outside, which means water is going to move out. As the water moves out, the cell literally dehydrates, causing the cell to shrivel up. Okay? And that is what we call plasmolysis. The cell starts to shrivel up on itself and shrinks to nothingness. Okay? And of course, if you look here, both of these result in a change in shape. And guess what? A change in shape results in a change in function. Yay. All right. So now that we get that, we can move on, hopefully. But there is one thing that I do want you to remember. In a hypotonic solution, the solution has more water. There's a higher concentration of water, but a lower concentration of solute. Okay? In an isotonic solution, there's an equal concentration. And in hypertonic solution, we have more solute, which means we have less water. So that means that out here in the environment, there's actually a lower concentration of water. And of course, remember, we go from high to low. So the cell has a higher concentration of water than the outside environment. We're going to talk about the term turgor and plasmolysis. The pressure that is exerted on a cell and its membrane from the inside out is called turgor pressure. Okay? This occurs in a hypotonic solution because as water flows into the cell, the pressure inside the cell starts to push outward, thus giving the cell a stiffer appearance. Now, if you recall from our original conversation about organelles. We talked about that central vacuole in plant cells. If we add water to a plant that's, say, wilted, and it starts to stiffen up, right? What we're doing is increasing the turgor pressure. As we fill up that water, the cell starts to stiffen up. We are increasing turgor pressure by increasing the amount of water going into the cell. Now, the opposite of turgor pressure is plasmolysis, and that is the negative pressure of losing water. And of course, if we put something in a hypertonic solution, we cause plasmolysis to occur, and that will result in wilting or shriveling up from the cell. And if you remember the blood cell, or look back in your notes at the blood cell, that first cell in the hypotonic solution, its turgor pressure went up so high that it exceeded the cell's ability to hold it all in, thus it lysed or destroyed itself. In plasmolysis, the cell lost so much turgor pressure that it decreased. Turgor pressure and plasmolysis are incredibly crucial, particularly in plant cells, because remember, plants don't have bones. So water really acts as the structural component that keeps them nice and stiff. If a plant, like a house plant, and if you look back in the room there, you see all of them, if the turgor pressure drops too low, the plant's going to wilt. Okay? Most plants we can add water to, and as the water infiltrates the cells, the turgor pressure will go back up, and ultimately, voila, we have the cell back. All right? Let's go back and try to knock this thing out. Last thing we'll talk about is facilitated diffusion. In this case, some molecules are simply too large to fit through the plasma membrane. Luckily, we've already studied the plasma membrane and therefore know that even though the concentration gradient is their favor, they may not have a way to get in and out, so the carrier proteins that are in that membrane can open and close like a door, letting the molecules through. If you remember when we studied the plasma membrane, we showed you that fluid mosaic model, and we showed you the two layers of phospholipids. But remember those big purple-like proteins that we showed you in that diagram? Those things can open and close like doors. So when the door opens, diffusion takes over. That means there's a higher concentration on one side of the cell, so these bigger molecules are going to go through the rules of diffusion. They're going to move from an area of high concentration to an area of low concentration. This is called facilitated diffusion. This is considered passive transport because the cell isn't actively moving these things. What they're doing is simply opening a door and letting things flow through on their own. They're basically just giving it an opening to come through, okay? But facilitated diffusion happens in the direction of the concentration gradient. Now, let me tell you something, and this is what gets people confused. What's the difference between active transport and passive transport? Well, let's take our car back, for example. Notice that when I slide my car down the ramp, once I let go, I don't have to do anything. It moves on its own. But if I wanted the car to go up the hill, I have to push it. I've got to provide energy to get it back up the hill. So if I want to go against the concentration gradient, instead of going down, which takes me no energy, if I want to go up, that's going to take energy, and that's active transport. All right, and that's another story for another day. But that is the ultimate difference. If movement occurs without the cell using energy, that is passive transport. Cell doesn't have to do anything, right? But if I have to push, that's going to be active transport. All right? Facilitated diffusion, by the way, is a form of passive transport because we don't have to use any energy. We just open the door. What does that look like? Kind of looks like something like this here, okay? This is a carrier protein. All right? And these cubes are obviously too big to fit through the plasma membrane, but what happens is that when they find this door, they move in that direction. Now, why are they moving in the upward direction instead of the downward direction? Because the concentration is higher here, down at the bottom, than it is up here at the top. And remember, diffusion tells us that things go from an area of high concentration to an area of low concentration. It's like magic. All right, so let's take a look at our objectives and see what we learned. First of all, diffusion tells us that molecules move from an area of high concentration to an area of low concentration. This is important because it allows things in organisms to evenly distribute so that all the cells in the body can get an equal share of the things that they need. Osmosis is the diffusion of water across a membrane. Why is water so important? Well, it is the most common solvent in biological organisms. Therefore, studying the movement of water is incredibly important. A substance that is isotonic has the same concentration of solute as the cells that we're referring to. Hypotonic means that we have a higher concentration of water but a lower concentration of solute. And hypertonic means we have a higher concentration of solute and therefore a lower concentration of solvent. So what would happen to a cell exposed to these conditions? Well, a cell exposed to a hypotonic solution will take in water because there's more water on the outside than there is on the inside. The cell will blow up, resulting in turgor pressure, and therefore could possibly blow up. If we are in a hypertonic solution, that means that there is more water inside the cell than outside the cell, which means water is going to move out, causing the cell to shrivel, or a process we call plasmolysis. And finally, in an isotonic solution, water will continue to move in and out at the same rate, resulting in a process that we call equilibrium. And finally, facilitated diffusion is basically the cell opening a door in its membrane to allow large molecules to fit through along a concentration gradient, meaning from an area of high concentration to an area of low concentration. Active transport is the movement of materials against the concentration gradient, which means that maybe there's some stuff on the outside and there's too much stuff on the outside, but there's stuff on the inside of the cell that we still want to get rid of. Well, that means we would have to move it against the concentration gradient, which means we are going to have to use energy. And that's the ultimate difference between all the things we talked about today, which is passive transport, and active transport. Passive transport, all of these things will happen on their own. The cell doesn't have to spend any energy. It's free. However, active transport does require energy on behalf of the cell. I hope you've enjoyed our time together. I feel like Mr. Rogers. I should go get my little sweater and put on my slippers. It's been nice to have you. Thanks for being my neighbor. Anyway, part 3 of your study guide is due for homework. Get those questions answered. We'll be checking those when I get back. If you need to watch this over, please feel free to do so. If you want to watch it at home, go to www.mrdocsonlinelab.com and click on podcasts, and there you can find it all pretty and happy right there on the internet. All right. Work on that study guide and have a good time, and I'll see you next time I'm there. Later, dudes.